See, I got to record this for Manny and the Addie and Ryan. I don't know why I said Manny. So what is power? It's the rate at which work is done, okay? So it's the same amount of work. I want you to think about this from the right perspective. It is the same amount of work to lift a box straight up onto a dock or to walk a box up a ramp. But it doesn't take as much power to walk the box up the ramp or shove the box up a ramp as it does to lift it and put it up there, does it? You know that's the case. I would much rather roll a big heavy stone up a ramp than to have to pick it up and put it up there. It's a big difference. And the difference comes in with the power. It's work over time. It takes us a lot longer to get the ball up the ramp than it does just to lift it. Therefore, it takes much less power. We're taking the same amount of work and dividing it by a much bigger number. Make sense? So power is really the name of the game to getting stuff done more easily. So power is the rate at which work is done or energy is transferred. So I want you to think about this. P, power, big P, is equal to work over the change in time or the rate at which energy is transferred. So change in energy, which is work, isn't it, over time. So what is work? Force times distance. So let's look at this. So power can also be defined as force times distance over delta T. Well, what is distance over time? Velocity. So it can also be defined as force times velocity. All right. Now, Physics C stuff, though, look what it says. Specific Physics C specific stuff. If we've got delta T and delta E, then we also know that power can be defined as what? dE dt or dW dt, can't it? Or since V and F are vectors, it could also be defined as F dot V. Remember dot products with vectors? F dot V. So what is the unit of power? Do you know what the unit of power is? Well, horsepower is sort of archaic. The energy coming into your house, which is the unit of power, watts. Kilowatts, really, because we use so many of them, but watts, which is W, big W, okay? Horsepower, just so you know, if you have horsepower, that's 746 watts. There's your conversion. So you probably sometimes need that conversion because we do still rank things according to their horsepower, which is kind of weird. Efficiency is epsilon. And that is the power used divided by the power supplied. Think about that. Doesn't that make sense? If something's really efficient, it does not use very much of the power it does not use much compared to what's supplied. If it's very inefficient, it uses a lot of what's supplied. Okay? So let's look at an example. We got an elevator lifting 70 kilogram people 3 minutes or 3 meters in 1 minute. How much power is required? Power is what? In this case, W over delta T, right? Well, what is W? Force times distance over change in time. Would you agree? Well, what's the force? 20 of them, right? So 20 times 70 times 9.8 over a 3 meter distance divided by 1 minute, which would be what? 60 seconds. So I want you to think about what watts, how else watts could be expressed. Watts would be Newton meters per second. Doesn't it work over time? So there's one way it could be expressed. Energy is what? Joules. So it could be joules per second. So what do we get? 20 times 70. I get about 686 watts. Okay? Now what's the efficiency? Oh, it says 36% efficient. How much power is needed to be supplied? So the efficiency is 0.36, correct? Well, that's used divided by supplied. Used is 686, isn't it? Power supplied, we don't know. So power supplied would simply be 686 divided by 0.36. $1,905, right? 0.6. So about 1,900, yeah, we'll do that. Watts. Okay. Now, what's the difference? It says find the instantaneous power to a 5 kilogram mass at times t equals 5 seconds, given that x is 5 sine 0.2 t. So, to find the power, we know what? Power is what? They've given us an x. They've given us that. Which formula?
FV.
Yep, FV. F dot V. Well, can we find V? We've got X, don't we? So V of t is equal to what? 0.2 times 5, right? Cosine, that would be negative because it's cosine. Sine to cosine is negative. Cosine 0.2t. No, positive. Be positive. Sorry. And we might as well go ahead and find A of t because we need what? Force? So that's going to be 0.2 times 5 is what? 1. So it's just going to be cosine of, I'm sorry, this one's just going to be what? Cosine 0.2t. Okay, so now this is going to end up being what? Negative 0.2 sine 0.2t, correct? How did I know I needed to take that? Because force and velocity, we got to find the force. Force is what? ma, so this is going to be ma's A of t, times v, which is going to be v of t, right? So we know the mass, that's the easiest part, 5. A of what? 5 seconds. So A at 5 is going to be negative 0.2 sine 0.2 times 5. So that's what? Sine of 1? And that would be radians, right?
Negative 0.168.
Okay. And we need V of 5. So that's just going to be cosine of 1, basically. What's cosine of 1?
0.54.
So we have 5 times negative 0.168 times 0.54. Negative. About 0.45, 0.454 watts. Okay? What do you think? All right, so let's look at the last one right here. Example C, it's a little more involved. We've got a golf cart, battery supplies, 1,200 watts of power, 80% efficient. Car travels at a constant speed of 9 meters per second, so we've got a velocity. Mass of the cart and the rider is 350 kilograms. What's the force of friction on the cart? Ooh, this one's so interesting. So the first thing we need to know is, let's go with this. We've got battery supplied, 80% efficient, so we need to know how much is used, don't we? So efficiency is equal to P used divided by P supplied. So we need to know the power used is equal to what? Going to be 1,200 times 0.8, which is indeed 960 watts, isn't it? So we've got that. Notice the next thing we do is a free body diagram. Got mg, got normal force, got the motor supplying a force, and then friction. Okay? This motor supplying force is the one we need, isn't it? Can we get that from the power we used? What do we know about P? P is equal to F times V. So the force of the motor is going to be P divided by V. So that's going to be 960 divided by what? Velocity? 9? 960 divided by 9. (106.7) or 107 newtons. Okay. It has a constant velocity, which means the acceleration is 0, which means the sum of forces is 0, which means what? Force of friction, the sum of forces, which is 0, is equal to what? The motor minus the force of friction. So what is the force of friction equal to? Then it just becomes Newtonian mechanics again, doesn't it? All right. We think about if there's anything else I want you to do before we look at that problem set that I gave you. Okay? That problem set is an additional expansion on what we're talking about here. Forces. Okay? Thinking about that. Find it first. Where did I put it? Actually. It's like, okay, I've got this all organized and I know exactly what I'm doing today, and now I can't find it. I have too many things in my life. I have too many stacks of paper, guys. Maybe I put it here. I bet I did. Yes, I did. Because I am not completely idiot. All right, the 9099 test question. This question is a free response question from the 99 Physics C test. it had 4 parts to it. Part A, B, C, and D. Okay? So take a look at what it said. The Sojourner rover shown in the sketch above was used to explore the surface of Mars as part of the Pathfinder mission in 1997. Use the data in the table below to answer the questions that follow. Determine answers for tests done on Earth. So the Sojourner data gave the mass of the Sojourner vehicle 11.5 kilograms. The wheel diameter was 0.13 meters. The stored energy available was 5.4 times 10 to the 5th joules. The power required for driving under average conditions was 10 watts. Do you see why there's a big, it's important to know if you're sending something out into space, you got to know how much energy you have available, because you're not going to get any more, are you? Necessarily, if it's batteries, which it usually is. And then the power required for driving. And then the land speed, 6.7 times 10 to the negative 3rd meters per second. All right. So it says, assume when leaving the Pathfinder spacecraft, Sojourner rolls down a ramp inclined at 20 degrees to the horizontal. The ramp must be lightweight but strong enough to support the Sojourner. Calculate the minimal normal force that must be supplied by the ramp. So what's the first thing you need to do here? So do one. Y'all work together on this if you want to. What is that going to look like? What needs to be adjusted here?
Split mg into components.
Okay, so we've got theta here. So we've got theta here at a right angle, going this way and this way. So this is going to be mg cosine, and this is going to be mg sine theta, correct? All right. Now what's next?
Sum of forces.
Okay. Sum of forces is equal to ma, correct? All right, so, but what is that going to be vertically?
Mg cosine theta minus
Okay.
force.
Mg, yeah, it doesn't matter. Because what's it all equal to? What is ma? What does this become?
Mg.
No, it's vertical. It's what? Yeah, it's 0, isn't it? It's at equilibrium vertically. It's only moving horizontally, isn't it? According to what we did. Remember, we defined this to be y and this to be x. So all the motion is in the x direction, isn't it? Going down. So that's 0. So that's why it didn't matter which one of those went first. So what is the normal force, which would be the weight, wouldn't it? What's going to be equal to?
Mg cosine theta.
Yeah. Okay, so that's part A. Mg cosine theta. Now, plug in some numbers, because they gave us numbers, didn't they? And figure out what that is. Okay, 106 newtons. Don't forget to put units on, please. All right, so part 2. What's the net force on Sojourner as it travels across the Earth's surface at a constant velocity? Now, guys, you may be wondering, why did she give us this problem? You tell me why I gave you this problem. It's not a tricked question. Yes, thank you. Why? How come?
Because it's moving at a constant velocity.
Yeah, net force, which is equal to ma, constant velocity, a is 0, so the net force is 0. So what does that mean? Force of friction must be equal to what? Because there's going to be friction here, isn't there? Yeah, force the motor. Sure enough. All right, so 3. Determine the maximum distance that Sojourner can travel on a horizontal Earth surface using its stored energy. So here we've given you the clue. Stored energy. What is stored energy, guys? Go back to the first page of your notes and look at what we said. What did we do? We said power was either what? Energy transferred, right? Work done, or rate at which energy is transferred or work is done. So that is going to be what? Yeah. Work over what? Time. So we got to find time, don't we? Do we know time? We know speed. We don't know time, do we? Can we find time here? Do we know the power? Do we know the work or the stored energy? Because this could be just as easily called E, couldn't it? And didn't they give that to us? So can we find time? Why do we need time here, guys? Let's approach this backwards. What are you trying to find? Distance it can travel. So we want to know delta x. So delta x is going to be what? V times t? Wouldn't you agree? Well, I need to know t. I've got v. I need to know t. That takes me to figuring out the other clues, which is, oh, hey, they gave me power and stored energy. Bing! I know those. So find t. What's t going to be here?
E over P.
Yeah.
Stored energy divided by power.
Yeah. T is going to be E over P. So we've got what? What is E?
5.4 times 10 to the 5th.
10 to the 5th divided by P, which is 10. So this is going to be what? 5.4 times 10 to the 4th seconds. That's cool. This is where we look at it as joules per second over what? I'm sorry, this is joules per second, and this is just joules, right? So then it comes up, becomes seconds. That's a lot of seconds. It'll run a long time, right? All right, so now let's figure it out. What's the velocity?
7.6 times 10 to the negative 3.
5.4 times 10 to the 4th seconds leaves me with a bunch of meters. So what'd you get?
400 G. That doesn't seem fair.
6.7 negative 3 times 5.4 to the 4th. I got 362 meters. Did you put 7.6 or 6.7?
I put 7.6.
That's why. It's 6.7 if you look at it. I think you just had a little dyslexic moment there. All right, so now it says, what happens if 0.01% of the power for driving is expended against atmospheric drag as it travels on the surface? Calculate the magnitude of the drag force. Oh, okay. So we know how much power it has. We know how much of that is expended on drag. So let's figure that out. And we know what velocity it goes. So we're still doing P equals F times V, aren't we? But this P is going to change. This P is now what? 0.01% of 10 watts. So that's what? 0.0001 times 10. That'll be the force of friction or drag times the velocity, right? And we know the velocity is, what, 6.7 times 10 to the negative 3? So we can find it. Is it going to be much? 0.0001 times 10 divided by 6.7. That is not much. 0.149 newtons. What do you think? Power is almost always, if you see it in one of these types of questions, involved with efficiency. It'll ask you how efficient is a motor. It'll ask you if the motor is only this much efficient, how much power, or how fast can it run, or things like that, okay? Now, if you look forward to